Imagine trying to win the multi-trillion-dollar global semiconductor race, but without building a single factory.
Right. It sounds impossible.
Yeah, I mean, we're talking about entering literally the most fiercely competitive, hyper-expensive industry on the planet. This is an arena where nations routinely drop, tens of billions of dollars just to pour the concrete for one single fabrication plant.
Oh, easily.
So today, we're taking a deep dive into a strategy that suggests a developing tech nation can realistically, well, bypass that massive financial barrier.
It's a completely different playbook.
Exactly. The proposed method isn't about outspending the giants, it's about outmaneuvering them. By focusing on something so microscopically small, it honestly almost defies logic.
Yeah, we are looking at a complete inversion of the standard geopolitical tech strategy here.
Right, and we're pulling our insights today from a really fascinating interview. It's titled Kung Nek Ung Ten Vietnam.pdf, featuring Dr. David Nghiem.
And just to give you some context on his perspective, because it's important, Dr. Nghiem spent over 2 decades doing really heavy-duty research and development at places like Qualcomm, Medtronic, Harris Corporation.
The heavy hitters.
Yeah, the absolute bleeding edge of radio frequency integrated circuits and antenna technologies. And his fundamental argument is that a country like Vietnam shouldn't try to beat established tech superpowers at the manufacturing game.
Because they can't.
Right, they can't.
Yeah.
Instead, they need to target this highly specific, intellectually demanding choke point, which is the design of on-chip antennas.
Okay, let's unpack this, because my immediate reaction to this strategy is just, well, skepticism.
Sure.
We constantly hear that chips are the new oil, right? So the instinct is, well, if you want to control the new oil, you need to build the oil rig. You need the physical infrastructure.
Yeah, the factories.
Why would a nation actively choose not to build the massive factories that physically produce, the world's most critical hardware?
Yeah. Well, the problem with that oil rig approach in the semiconductor world is what we call the fab trap.
The fab trap.
Yeah, fab as in fabrication plant.
Yeah.
Because a modern semiconductor fab is arguably the most complex manufacturing environment human beings have ever created. I mean, it requires an upfront capital investment of maybe $20 to $30 billion.
Just to start.
Just to open the doors.
Yeah.
But honestly, the money is actually the easy part.
Wait, really? $20 billion is the easy part?
Yeah, because a fab requires a perfectly synchronized ecosystem. You need an unbroken, ultra-pure water supply. You need a power grid that never fluctuates, not even for a microsecond.
Because if it does.
If you get a sudden voltage drop, you can ruin months of silicon wafer production. It just goes in the trash. Plus, you need a localized workforce of thousands of highly specialized technicians.
Right.
So if a developing nation attempts to build this from scratch today, they are entering this brutal, low-margin war of attrition. And they're up against countries that have a 40-year head start.
And fully depreciated equipment, I imagine.
Exactly.
So it's basically like deciding you want to get into the restaurant business, right? So you take on billions in debt to build the largest, most expensive commercial kitchen on Earth.
That's a good way to look at it.
Only to realize you still have to convince people to hire you to cook their food. And you're competing against kitchens that have been operating flawlessly since, like, the 1980s.
Yeah, that kitchen analogy perfectly highlights the core economic vulnerability of just doing pure manufacturing.
Yeah.
Because if you just build the kitchen, you are essentially renting out your labor and your machinery.
You're just a landlord for tech.
Right. You don't own the underlying value. So Dr. Nghiem's proposal is to become the master chef who writes the recipe instead.
Oh, I like that.
I mean, if we connect this to the bigger picture, look at companies like Apple or Qualcomm. They don't actually physically manufacture their own silicon processors.
Right, they outsource it.
Exactly. They engineer the architecture. They own the patents. They capture the overwhelming majority of the profit margins through intellectual property.
And then Taiwan or South Korea just does the physical printing.
Exactly. Specialized foundries do the heavy lifting.
So the argument here is that Vietnam needs to run the Apple playbook. Just completely bypass the crushing overhead of the physical factory and concentrate entirely on the blueprint.
Yeah, by prioritizing design, a developing tech sector can achieve an incredibly high-value return on a much smaller targeted investment.
Makes sense.
The goal is to generate revenue and cultivate a highly skilled engineering workforce at the same time. And over time, that IP gives you the leverage to sit at the table with the global giants as an equal partner.
rather than just being, a low-cost assembly hub for foreign tech. Okay,
Exactly.
that makes perfect economic sense. But Dr. Nghiem doesn't just vaguely suggest designing chips. He gets hyper-specific.
Very specific.
He points to radio frequency integrated circuits, RFICs, and specifically the on-chip antennas. And here's where it gets really interesting, because the physics of this strategy seem completely paradoxical to me.
How so?
Well, we are talking about an antenna. When I think of an antenna, I think of physical size, like a radio tower, a satellite dish, even the old rabbit ears on a TV.
Right.
And the fundamental physics laid out in the source material states clearly that as an antenna gets smaller, its radiation efficiency drops. It simply cannot broadcast or receive as effectively.
Yeah, you are hitting on the fundamental physical constraint that makes this field so phenomenally difficult and therefore, so valuable.
Because it's hard to do.
Extremely hard. An antenna works by converting electrical currents into electromagnetic waves and vice versa. And for that conversion to happen efficiently, the physical length of the antenna typically needs to correspond mathematically to the wavelength of the signal it's trying to catch.
Okay.
So when you try to shrink an antenna down to fit onto a microscopic piece of silicon, you are fighting a brutal battle against physics.
The efficiency just drops.
It plummets. Most of your signal energy gets lost as heat rather than radiating outward.
Wait, it gets worse though. Because not only are you shrinking the antenna to a size where it barely functions, but you are also burying it inside a microchip.
Yep.
And a microchip is densely packed with metallic structures, wiring, transistors. The text points out that these surrounding metals cause severe interference.
They absolutely do.
The metal literally blocks or distorts the signal. So why on earth is this the chosen strategy? I mean, it sounds like you are fighting gravity. You are designing a compromised antenna and then placing it in the most hostile electromagnetic environment possible.
Well, that intense difficulty is exactly the barrier to entry. Dr. Nghem's approach relies on treating the microchip and its surrounding environment as a single unified ecosystem.
Instead of just seeing the metal as an obstacle.
Right. High-level RF engineering involves turning that potential interference into an asset.
I honestly don't get how that is even physically possible. Metal blocks radio waves. We know this. You go into a metal elevator, you lose your cell service.
Sure, but think about a flashlight. If you just have a bare light bulb, the light scatters weakly in every direction. But if you put a shaped metal reflector behind that bulb, you gather all that scattered light and focus it into a powerful directional beam.
Oh, wow. Okay.
In on-chip antenna design, engineers use the surrounding metallic structures of the chip in a similar way. Through incredibly complex mathematical modeling, they shape and position those microscopic metal components to act as, well, parasitic directors and reflectors.
So they use the hostile environment to guide the signal.
Yes, they guide, shape, and amplify the electromagnetic signal, forcing it to go exactly where they want it to go.
So the interference literally becomes the magnifying glass.
Precisely. And pulling from the text, there are 3 critical technical hurdles an engineer has to overcome to actually pull this off.
What are they?
First is impedance matching. Imagine trying to connect a massive high-pressure fire hose to a tiny garden hose.
It's going to burst.
Exactly. The mismatch in size creates massive resistance. Water splashes back violently, and very little actually flows through. In electronics, if the impedance, the electrical resistance of the microchip, doesn't perfectly match the impedance of the antenna, the electrical signal bounces back into the circuit.
It never radiates out.
Right. It just turns into destructive heat.
So impedance matching is basically like smoothing out the transition so the energy flows seamlessly from the circuit into the air.
Yes, and it requires meticulous geometric adjustments at a microscopic scale.
Wow. And the second hurdle.
The second is maintaining that overall radiation efficiency despite the tiny physical footprint, ensuring enough energy actually leaves the chip to be useful.
Makes sense.
And the third is tailoring the emission characteristics. So shaping that beam, like the flashlight reflector, for specific applications, whether it's a wide net for Bluetooth or a highly focused beam for a radar sensor.
Let's layer in the next massive complication the text brings up, because this blew my mind. The impending transition to 6G and terahertz frequency bands.
Oh yeah, this changes everything.
Right, because we all want faster data, which means pushing telecommunications into higher and higher frequencies. But Dr. Nghiem points out a terrifying side effect of these terahertz frequencies.
Yes, he does.
At these incredibly high speeds, the semiconductor materials themselves, like the actual silicon start absorbing the electromagnetic energy.
The substrate of the chip literally becomes a sponge for your signal.
And even crazier, the tiny microscopic transmission lines that connect different parts of the chip can accidentally start acting like unintended antennas.
Yep.
They just start broadcasting signal noise everywhere. You end up with a chip that is essentially yelling at itself, drowning out the actual data in this chaotic electromagnetic soup. Controlling that seems virtually impossible.
It did a nightmare for signal integrity, I won't lie. But Dr. Nghiem identifies a massive silver lining inherent in the physics of 6G and terahertz frequencies.
There's a silver lining to the chip yelling at itself.
Well, there's an inverse relationship between frequency and wavelength. As the frequency goes higher, the physical wavelength of the signal gets shorter.
Wait, shorter wavelengths mean you don't need a large physical antenna to catch them?
Exactly. The physics suddenly start working in your favor regarding size. Because the terahertz wavelengths are so incredibly short, the optimal physical length of the antenna becomes microscopic.
Oh,
It
wow.
actually becomes physically easier and more natural to integrate the antenna directly onto the chip itself. So while the energy absorption and the noise are immense hurdles, the transition to 6G makes on-chip antennas not just possible, but fundamentally necessary.
That is wild. So we have this brutal physics challenge, but mastering it creates a really unique economic opportunity.
Right.
But then the text pivots to an implication that completely reframes the stakes here. Because mastering this technology isn't just about giving you faster download speeds or creating a profitable export.
No, it's way bigger than that.
It fundamentally changes who holds the keys to national security.
What's fascinating here is that an antenna is a hardware component, sure, but its strategic value scales directly to sovereign defense.
How so?
Well, when we talk about cybersecurity, we usually think in terms of software, right? Firewalls, encryption, antivirus programs.
Yeah, lines of code.
But the antenna operates at the physical layer. It is the absolute first point of contact for receiving and transmitting any wireless signal.
So it's basically the front door and the bouncer for a nation's entire digital infrastructure.
That is a great analogy. If you control the literal gateway the signal passes through, you dictate what enters the system before the software even knows it's there.
Right.
Pulling from the source, Dr. Nghiem explains that mastering this physical layer allows a country to proactively control its signals. If you design the antenna, you design the noise filtering mechanisms baked directly into the silicon.
So you can build hardware-level protection that physically rejects malicious frequencies or isolates secure communications.
Exactly. A software patch can always be hacked, reversed or spoofed by a clever enough adversary. But a physical hardware filter designed at the sub-millimeter level to only accept specific electromagnetic signatures.
That's practically bulletproof.
It is vastly more robust.
It creates a foundational level of technological autonomy, because if a nation relies entirely on foreign-designed chips with foreign-designed antennas for their military communications, power grid sensors, or cellular networks...
They are operating with an inherent, unpatchable vulnerability.
Right. They have no idea what hardware-level Trojans or backdoors might be baked right into the silicon.
To truly secure your networks in the 21st century, you must own the core technology at the physical layer. You cannot outsource your foundational hardware design and expect to maintain sovereign security.
Which logically brings us to the operational bottleneck. Because, okay, we know what needs to be designed, we know the physics of how it works, and we totally understand the geopolitical necessity. But how does a developing tech nation actually build the workforce to execute this? We're talking about a field that requires an elite understanding of electromagnetics and quantum mechanics.
Well, the raw material is actually there.
Yeah.
The text highlights that Vietnamese engineering students already possess a very strong foundational baseline in mathematics, electronics, and theoretical physics.
Okay, so the roadblock isn't brainpower.
No, not at all. It's the physical infrastructure required to translate that theory into practical engineering.
Like specialized lab equipment.
Specifically testing equipment. Traditionally, to measure the efficiency of an antenna and see if your design actually works, universities and tech companies need anechoic measurement chambers.
Oh, I've seen pictures of those. The crazy rooms with the spikes on the walls.
Exactly. They are massive room-sized facilities completely lined with highly specialized pyramid-shaped foam that absorbs all stray electromagnetic waves.
Just totally isolates the room.
Right. It isolates the antenna so you can get a perfectly clean measurement without background radiation interfering.
But I'm guessing those are not cheap.
They cost millions of dollars to build and maintain. Most universities in developing nations simply cannot afford them. And this creates a devastating gap in the education system.
Because they can't test their work.
Right. Students spend 4 years memorizing Maxwell's equations and learning abstract theory, but they never get to physically build and test a real antenna. They graduate with a head full of math and zero practical intuition.
So what's the workaround?
Dr. Nghem's workaround is fascinating. He founded an organization called the Talented Minds Agency, or TMA, designed to mentor young talent and connect them directly to international R&D pipelines.
Okay.
And his primary tool is a proprietary testing method he developed to basically bypass the need for those massive multi-million-dollar chambers.
Wait, he just bypassed the millions of dollars of hardware?
He essentially democratized the testing process. While the source text doesn't give away the exact proprietary mechanics, the engineering principle behind bypassing large anechoic chambers usually involves a combination of highly targeted near-field scanning and advanced computational algorithms.
So instead of a giant room, you do what?
Instead of relying on a massive, physically isolated room to capture the far-field radiation pattern, you take hyper-precise measurements literally millimeters away from the chip.
Oh, wow.
And then you use advanced software modeling to mathematically extrapolate how that antenna will perform in the real world.
So you substitute massive physical infrastructure with advanced mathematical modeling.
Exactly. You significantly lower the barrier to entry for innovation. But there is a claim in the text that requires some real scrutiny, honestly.
Let me guess. The timeline.
Yep. Dr. Nghiem states he can train a fully functional antenna design engineer in just 6 months.
Yeah, I have to push back hard on that.
It's a bold claim.
I mean, wait. We just spent 15 minutes detailing terahertz substrate absorption, impedance matching, and parasitic directors. The idea that you can take someone and make them competent in this highly complex, specialized field in 6 months sounds like a massive exaggeration.
I completely understand why you'd say that.
A traditional master's degree in this field takes years.
It sounds impossible if you look at it through the lens of traditional academia. But the text explains the mechanics of this accelerated timeline. And it works precisely because he isn't teaching them the foundational math.
Because they already know it.
Right. The students already have that baseline. What the TMA training program does is ruthlessly strip away the abstract, purely academic theory that pads out a traditional university syllabus.
Oh, okay. So it's structured less like a graduate program and more like, what, a high-intensity corporate boot camp.
Exactly. The training deliberately mirrors an intense corporate R&D workflow. Dr. Nghiem doesn't ask students to write theoretical papers on radio wave propagation.
He gives them real problems.
He gives them a specification sheet for a commercial problem. Say, designing a Bluetooth antenna that fits inside a smartwatch casing without losing signal when it's pressed against a human wrist.
That's highly practical.
The students jump straight into industry-standard CAD software, design the architecture, and use his accessible testing methods to immediately iterate on their failures.
So they learn by troubleshooting real impedance mismatches, not by reading about them in a textbook.
This iterative, hyper-practical loop accelerates the learning curve exponentially. I mean, think about it. The global semiconductor industry doesn't need graduates who can recite theoretical physics.
They need people who can build things.
They need engineers who can open a software program, design a functional chip that meets a client's thermal and spatial constraints, and get it ready for production.
Right.
By focusing entirely on transforming theoretical knowledge into tangible commercial products, a 6-month timeline for a student who already knows the math actually becomes highly realistic.
So what does this all mean? If you successfully deploy this low-cost testing and this rapid 6-month corporate training, you suddenly have a cohort of elite RF design engineers.
A very valuable asset.
But what keeps them there? If a developing nation mints these brilliant minds, but doesn't have the ecosystem to employ them, well, those engineers will just get on a plane to Silicon Valley or Taipei.
That is the classic brain drain problem.
You've just subsidized the R&D departments of your competitors.
Cultivating the macro environment is the final, arguably most difficult piece of Dr. Nghem's blueprint. You cannot just train engineers in a vacuum. You have to build a gravity well to keep them there.
A gravity well.
Yeah. And his ultimate vision is to establish a dedicated, world-class antenna design center physically located in Vietnam.
So central hub designed to reverse the brain drain?
A hub that serves multiple functions. It executes commercial contracts, it drives continuous technology transfer, and critically, it serves as the training ground to teach the future trainers.
A self-sustaining loop.
It creates a self-sustaining loop of intellectual capital. But Dr. Nghiem makes it explicitly clear that private enterprise and universities cannot build this gravity well alone.
So the government has to step in.
It requires highly deliberate scaffolding from the government.
Yeah, the source outlines very specific policy requirements. The government has to provide aggressive tax incentives for domestic design firms.
Right.
They have to slash the red tape and tariffs associated with importing specialized research and laboratory equipment. But the most crucial policy intervention is on the demand side.
The market side.
Right, the government must actively encourage or even mandate that domestic tech businesses actually purchase and integrate the IP designed by this local center.
You have to solve the valley of death for new technology.
What do you mean by that?
Well, if a Vietnamese telecommunications company continues to buy all its network antennas from established foreign suppliers just because it's slightly cheaper or deemed less risky, the domestic design center will starve to death.
Oh, I see. There is no revenue to fund the next generation of R&D.
Exactly. The government has to act as a market maker. They have to guarantee a customer base in those fragile early stages to get the economic flywheel spinning.
So it's not just about education, it's about forcing the market to adopt the education.
And every major technological superpower in history has used this exact mechanism.
Really?
Oh, absolutely. They fiercely protected and nurtured their domestic innovation ecosystems through government procurement and localized market incentives until those domestic companies were strong enough to compete on the open global market.
So by artificially generating that initial demand, a nation can systematically step up the semiconductor value chain.
You start by mastering the isolated antenna. You use that revenue and expertise to co-design the broader radio frequency integrated circuit,
And then eventually you own the intellectual property for complete, highly complex systems.
rendering your tech sector indispensable to the global supply chain.
It is an incredibly pragmatic, almost surgical strategy. Let's look at the entire picture we've uncovered for you today.
A lot to take in.
It is. The narrative we are usually fed is that entering the semiconductor space requires a brute force financial assault. Building massive factories and competing on sheer scale. But Dr. Nhiem's blueprint proves that a developing tech nation doesn't actually need to follow those painfully expensive high-risk footsteps.
No, by identifying a severe technical bottleneck, the complex physics of on-chip antennas, and attacking it with specialized design rather than manufacturing, the dynamic completely shifts.
Yeah, they combine innovative, algorithmic testing methods that bypass the need for $1 million laboratories, right, with an ultra-practical corporate-style training pipeline.
Right.
And this allows them to leapfrog the manufacturing phase entirely and inject themselves directly into the highest value segment of the tech ecosystem, which is intellectual property generation.
It is honestly a masterclass in asymmetrical economic strategy. It demonstrates that precision, targeted education, and critical engineering can successfully outmaneuver sheer financial mass.
Which leaves a massive lingering implication to think about as you go through your day. If the barrier to entry for highly complex hardware engineering is falling, I shouldn't say falling, it's shifting.
It's shifting to software and math.
Exactly. If the testing can be done with advanced math instead of massive physical chambers, and the training can be compressed into hyper-practical boot camps, the geographic monopoly on high tech is going to fracture.
It's inevitable.
How will the democratization of elite hardware design shift the balance of geopolitical power over the next decade? Could the next dominant tech superpower be a nation we aren't even paying attention to right now, quietly mastering the microscopic blueprints while the rest of the world bankrupts itself, building giant empty kitchens?
The nations that figure out how to scale this intellectual capital will absolutely define the next era of global security.
It fundamentally changes the map. Thanks for joining us for this deep dive. Until next time.